Welcome back to Operating Systems Crashcast. I'm Victor, and with me as always is Sheila. Today, we're diving into a fascinating topic, multi-core programming.
That's right, Victor. As we continue our journey through threads, it's crucial to understand how modern processors with multiple cores have changed the game. Let's start with the basics. What exactly is a multi-core processor?
Great question, Sheila. A multi-core processor is essentially a single computing component with two or more independent processing units called cores. These cores can read and execute program instructions simultaneously, allowing for parallel processing. It's like having multiple brains working on different tasks at the same time.
That's a great analogy, Victor. And it's worth noting that multi-core processors have become ubiquitous. Your smartphone, laptop, and even some smart home devices likely have multi-core processors. But having multiple cores isn't enough on its own, right? We need to program for these systems effectively.
Absolutely. This is where multi-core programming comes in. It's the practice of designing software applications that can take advantage of multiple processor cores to improve performance. However, it's not as simple as it might sound. There's an important distinction to make between parallel and concurrent execution.
Could you elaborate on that, Victor? I think our listeners would benefit from understanding the difference.
Of course. Parallel execution is when multiple tasks are literally running at the same time on different cores. Concurrent execution, on the other hand, is when tasks are progressing by taking turns using the available cores. Both are important in multi-core programming, but true parallelism is what can lead to significant performance improvements.
That's a crucial distinction. Now, let's talk about some of the challenges in multi-core programming. One major issue is identifying opportunities for parallelism in algorithms and applications. Not all problems can be easily divided into parallel tasks.
That's right, Sheila. Another significant challenge is dealing with shared data. When multiple cores are working on related tasks, they often need to access the same data. This can lead to race conditions and other synchronization issues if not handled properly.
Absolutely. And let's not forget about load balancing. Ensuring that work is distributed evenly across all available cores. It's like trying to keep multiple assembly lines running at the same efficient pace.
Great point. Now, let's discuss some approaches to multi-core programming. One common method is to use threading libraries, which provide tools for creating and managing threads that can run on different cores.
Another approach is to use parallel programming models like OpenMP or Intel's threading building blocks. These provide higher-level abstractions that can make it easier to parallelize code without getting bogged down in low-level threading details.
Don't forget about message passing interfaces like MPI, which stands for Message Passing Interface. It's particularly useful for distributed systems, but can also be applied to multi-core programming. MPI allows different parts of a program to communicate and coordinate their actions by sending and receiving messages.
All great points, Victor. Now, what about the benefits and limitations of multi-core systems? We've touched on improved performance, but are there other advantages?
Definitely. Multi-core systems can be more energy efficient than single-core systems running at higher clock speeds. They also allow for better multitasking, as different cores can handle different applications simultaneously.
On the flip side, there are limitations. Not all applications can be easily parallelized, so some software might not see significant performance improvements on multi-core systems. There's also the challenge of increased complexity in software development and debugging.
Absolutely. It's a classic case of, with great power comes great responsibility. Multi-core systems offer tremendous potential, but harnessing that potential requires careful design and implementation.
Well said, Victor. As we wrap up, let's recap the key points we've covered about multi-core programming. 1. Multi-core processors have multiple independent processing units or cores. 2. Parallel execution runs tasks simultaneously, while concurrent execution alternates between tasks. 3. Challenges include identifying parallelism, managing shared data, and load balancing. 4. Approaches include threading libraries, parallel programming models, and message passing interfaces. 5. Benefits include improved performance and energy efficiency. but limitations include increased complexity and the need for parallelizable applications.
Great summary, Sheila. Understanding these concepts is crucial for anyone working with modern operating systems and applications. Thanks for joining us, listeners, and stay tuned for our next episode where we'll explore multi-threading models.